We have seen how to convert your ad hoc command into a playbook and how to store the output of a task. Because by default, playbooks are designed not to bring the output, because playbook could consist of multiple plays. Right? We can write large playbooks consisting of big number of tasks. So outputting showing the output of all these tasks will become like very redundant. There will be so much to look at. So we don't want to do that. So by default, the output is disabled. If you want to specifically see the output, we'll have to use the register keyword to store the output in a variable, and use the debug module to display the value of this variable. And we have seen config module, which is used to send config commands. I could find my HashiCorp vault installation. We'll go there, but before that, it's not very perfect installation. But before that, we'll cover Docker. Okay, Docker is, I felt more than Vault, Docker is more important when it comes to, because Vault is one such tool where secrets are stored. We've already seen one such, right? Ansible Vault. Both work on the same lines, except that HashiCorp Vault being a dedicated Vault kind of software, they offer UI on top of it, and you can manage your key stores and keys, etc. via UI. Other than that, whatever we have seen in Ansible holds pretty much same. Okay, so we'll go to Docker now. Docker is an open source platform that allows developers to automate the deployment, scaling, and management of applications inside lightweight and portable containers. Right? There are a lot of technical terms that allow developers to automate the deployment, scaling, and management of applications inside a lightweight portable containers. Now, how and why exactly this Docker was born is, in the development world, right? We used to have developers working on some software. After they finish, they will give it to the testing team, the quality assurance team, to get it tested. QA guys will test it, ensure that it is working. They deploy it to staging or pre-prod server, where further test, acceptance kind of test will be done, and finally the client will say, okay, yes, I accept this product or I reject this product. Go, no go, we call it as. If the client says go, we will finally deploy it in the production environment. Right? Now, it so happens that developers, they don't intentionally do it, but while working on complex projects, right, their systems, the development servers, have so many things which will, so many frameworks installed, so many tools already set up, so many shortcuts taken to get their work quickly done. Right? So most of the things will work fine on development environment. When they run it, it works fine because they would have been setting up everything that way. Now, when they have to give this software copy to QA guys to be tested, they won't be able to figure out what all to give along with the software for it to work. Any configuration files, any setting files, any folders which have to be which they would have forgotten to include in the build, and so on. So they give something to the QA guys, And QA guys will say that yes, it is not working, and when we deploy it in the QA environment, it is not working. The developer says it is working in my environment. You please check. The QA guy says no, it's not working in my environment. Then the play comes, looks at the logging, debug messages, finds out that oh okay, he missed some file, or he missed updating some settings in some file, or for example, like let's say there's a database connectivity that needs to be established. During the development, the developer would have pointed to some mini development version of the database which is running on their server, but that part they would have forgotten while giving it to the QA guys. So without setting up the QA environment, the database in the QA environment, they'll be trying to run it. And so these kind of things. So finally they figure out it, they manage to get it working on the QA environment. Then they ship it to the pre-prod or prod environment. The same story repeats. Again, there could be certain dependencies which have to be taken care of, certain prerequisites which have to be met on the pre-prod or the prod environments, which these guys would have forgotten to document, would have not taken care of. We'll end up with the same scenario, right? Working on one environment, not working on another environment because of missing dependencies is a very common and very critical problem in software development and delivery, right? So to address this issue, this concept called as containers has come up, because that is one reason what we just said. And if you see nowadays the kind of applications that are being deployed, there are multiple languages used, programming languages, multiple frameworks, multiple types of databases. So creating builds, working builds is a huge task. It has to properly take all these things, different frameworks, different languages, different databases, etc., into consideration while creating builds. And on that build has to be now deployed, right? So one client will say deploy it in my local data center. The other guy will say deploy it in my cloud. The other guy will say deploy it in my hybrid cloud, partly local, partly the data center, partly the cloud. Because in spite of all the security, all the assurances being given by the cloud platforms, people are still hesitant to put their sensitive data on the cloud. So some companies which are very specific about protecting their data, they follow the hybrid cloud approach, which means certain servers will still be in their on-premise data centers. Certain servers will be deployed on the cloud, and they establish bridge or tunnel, whatever network mechanisms to establish connectivity between these two. And of course, by applying appropriate policies, setting up firewalls, etc., etc. Right? So that your data is still safe in your environment. Only your applications are running in the cloud. So there could be varied types of deployment environments: private cloud, public cloud, hybrid cloud, and so on-premise data centers. So when we have to deploy the build which is created based on this multiple frameworks, languages, etc., on different deployment targets, again we'll run into the same issue, the challenges. How do you deploy? Even if you manage to deploy, how do you ensure that our application continues to be up and running? How do you monitor it? How do you track what is going on? Right? These are the challenges. So to address both these concepts, they have come up with this concept called as containers, which is a kind of virtualization. Right? So that's what here we are talking about. Automating the deployment. How it is done, we'll see when we talk about the containers. Right? So we are looking at a solution, a platform, which can be used by the developers to automate the deployment and scaling and management of applications inside lightweight portable containers. Containers are a form of virtualization technology. Right? So now we are no more talking about deploying on QA server, deploying on some other server. We are talking about creating a container, which is like a virtualized logical unit, which contains everything that is needed for your application to run. Then you just take that container, drop it wherever you need it. Of course, assuming that the container support is there. They enable applications and their dependencies to run in isolated environments. This is the crux. Applications and all their dependencies, whatever is required, they put them in an isolated environment and convert this isolated environment into a container. This ensures consistency across different systems and reduces conflicts between different software stacks. Right now, because everything that is required for an application to be to work properly is packaged into the same container. So wherever you go, you take this container, put it. It just has that container support platform. It starts working. Okay. Now, it sounds very nice, but what happens in the background? How this entire thing is made to work? And these are the components that are involved in it. And there is something called as a Docker engine, which is the core component of Docker. It is a client-server application which is responsible for building, running, and managing Docker containers. Right? We said the developers will be building a container with an application and all its dependencies. So who is the guy who does it? The Docker engine. Right? Docker engine is used to build the container, and is also used to run the container, and is also used to manage the container. And managing means bringing it down, bringing it up, upgrading, and so on. Docker client is like a CLI tool from where we'll be giving Docker commands like, okay, build, run, stop, start, delete, and so on. So Docker client communicates with the Docker daemon. Docker daemon is like a server which is running continuously in the background, trying to listen for any requests that could be coming. Right. So on the CLI, when we say Docker build something, the command is taken by this Docker daemon, Docker server. Now the communication between this front end and the back end, and the client and the server happens through REST API mechanisms. Okay. So that's what your Docker engine is about. Docker engine is a combination of Docker CLI as well as a Docker daemon. And Docker CLI, which is like a front end for or a command line utility to give the Docker commands, which are then accepted by a Docker daemon and the server component which is running in the background. So that both these constitute your Docker engine, which happens to be a core component of Docker. Then comes the container, right? The crux of this thing. Container is nothing but a lightweight standalone executable package. Right? What is a container? It's a lightweight standalone executable package that includes everything that needs to run a piece of software, including code, runtime libraries, system tools, whatever you need for an application to run successfully is packaged into this. And it is lightweight because normally if you see the core files which are used by applications to run are like very minimal. But because of the other dependencies, it becomes big. We cannot simply separate them out. But Docker does that. It creates a lightweight standalone executable package, including everything that is needed for a software to run, like code, runtime libraries, system tools, etc., etc. What is the advantage of containers is containers are isolated from the host system and from one another. Right? I've developed a web application, two web applications, for instance, in two containers. They both are isolated from each other. Each web application carries with it whatever is required, like a web server, an application server, and so on. Okay. So since they are isolated from the host, underlying host, which means the machine on which they sit, as well as among themselves, they are highly portable and they are consistent across different environments. Right? Because they are like self-dependent, I can simply take them and put them on any server where Docker is installed. The application will start running, and no more that business. I forgot to include this file. You need this additional piece of software for this application to work. No more such these things. If a container is properly built, if it is running on system A, you take it to system B where Docker is installed, deploy the container, bring it up, it should be up and running as it does on system A. Then image. Image is a read-only template which is used to create a container. Right? What is container? Container is nothing but a standalone executable package which consists of some things. Now, what all it should be consisting of should be specified as a blueprint, as a plan, right? As a specification. That blueprint or a plan or a specification is nothing but your image. Image is like a read-only template. Now, if you want to better understand images and containers, you can think of what happens in the virtualization world, right? We have a virtual machine and we have something called as a virtual machine template, right? Let's say you are asked to create 10 VMs which are identical to each other with some 10 tools installed. Application server, a programming language, something else, a list of 10 softwares have to be, let's say, installed, and 10 such VMs have to be set up. So how will you do? You won't go and create 10 blank VMs, install 10 OS on them, and then start installing 10 into 10, there's 100 softwares, right? What you'll do, you'll take one system, install OS once, install these 10 pieces of software once, ensure that the system, the VM that you created meets your specifications. And then what you do, you convert this VM into a template, which becomes static, right? Your VM is running, it's alive. From this live system, you create a template, which becomes like a static file. Then using that template static file, you create 9 more copies, 9 more instances of the VM. Bring them up, you have 10 VMs which are running with similar kind of identification. Same concept is used here. Docker image is a static file which specifies how your container should be, what all should be there in your container, how the container should behave. Then container is a running instance of an image. You take an image, you create a container from it, you run the container, then you get your container which is running up and running, where your application is up and running. Okay, so that's the concept of Docker images. Now, to create a Docker image, we need to tell what all we want to package into this. Finally, when we create a container from this image, what all files should be pushed into the container. So accordingly, we create a specification file, which we call it as a Docker file, which contains the instructions for creating the image. Okay. Docker file. A Docker file is a text file that contains series of commands and instructions to build a Docker image. It defines a base image. Now, when I say I'm creating a Docker image for, let's say, a Python application, right? Now, this Python application needs Python to be running. Now, you don't expect me, just because I said I'll be creating a self-dependent container, you don't expect me to rewrite the Python interpreter, entire Python language, right? Suppose I managed to do that. Python needs OS to run. So you won't expect me to write the OS components, right? what I'll do, I'll make use of existing stuff. So someone has created a Docker image with Python in it, Python Docker image for Python. Now I'm writing a Python application. My application needs Python to run. So what I'll do, I'll take the existing Python image and add my code and anything else which is required on top of what I have taken, the base image, what I have taken. Okay. Now the Python guys, whoever has created that Python image, what they have done, ultimately Python is also nothing but a bunch of files. For these bunch of files, they need to sit somewhere. They need the operating system level features. And right. So what they would have done, they would have used Ubuntu or some other operating system as a base image. On top of that, they would have installed Python. Just like how you take a VM, install Python, and then convert it to image. They take a Ubuntu image, create a container from that, run it. So your Ubuntu is running. In that, you install Python. Now your Python is running on top of Ubuntu successfully. Convert this into a image file, save it. So you get Python image like that. Then you take the Python image, which is nothing but Python and OS, mini OS combination. On top of that, you put your Python application related files. You publish that as an image. Okay. So a Docker file is a text file that contains a series of commands and instructions. It defines a base image. So that's the concept of base images. If I'm building something, I'll be using something as a base. Set up the environment to install software packages and copies the application code into the image. Okay. Now, just like how we have Python third-party libraries, right? There's a registry called as PyPy, Python Package Index. And in case of Ansible also, we have something called as Ansible Galaxy, which is like a online repository. From there, we can download the Ansible content, which is written by third-party guys and companies like Cisco. All these guys have written their own Ansible modules to simplify working with Cisco applications, Cisco devices. Same way, Docker also has the concept of online registry, which is nothing but a collection of images, right? So many people have developed so many Docker images. They have uploaded them onto this public repository called as Docker repository. So from there, we will be able to easily get whatever we want already. And Docker registry is called as Docker Hub. So this is your online registry, right? You already have all these images. These are all like whatever you see here are the Docker images, right? I want a simple web server. I don't have to reinvent the wheel. Like I'm creating a web application. I need some web server on which my web application will sit. So this is that web application. I'll take the data. I'll click here. That's opening documentation. This is the official Docker official image, which means the Nginx company has given me a Docker image, right? So the very concept of Docker images, right? It's like a template based on which I can create a Nginx container. what will Nginx container contain? Whatever is required for a web application, for this simple web application to be up and running, is there in this container. Is in this image, using which I can create containers. Okay, so like this, these are all, there are many, right? We can search. I want to work with databases, I have them here, right? PostgreSQL, MySQL, MongoDB, AI stuff, right? I need a Ubuntu image, right? I have it here. I need a Python environment for me to write programs, right? I have it here. Now this guy needs this guy or some other guy underneath, so OS. So he takes this guy and puts Python on top of it and publishes as another list. Like this, you have so many pre-created images are there, right? Even Grafana, which is like a visualization tool, there's a Docker image. Okay, so that is your registry. Containerization is nothing but the process of creating these images. Take some existing code, convert it into a Docker image, and we can upload it into our account by logging into our account into Docker registry, Docker Hub, and putting it into our own user space. So the architecture looks somewhat like this. This is your online registry, which we have just seen. We have Python, we have Ubuntu, this CentOS, I guess. We have different types of images which are available. So from here, this is your Docker host, the machine where Docker is installed. And from here, you connect to the registry, you fetch the Docker images. Using the Docker images, you create containers, right? These Docker images are like static files. From them, you create dynamic running instances called containers. Okay. All these tasks are done by this Docker daemon, which is like a server which is running. Now, on the client side, this is the Docker client, which is the CLI. We can use this kind of commands. Docker build to create this kind of Docker images. Docker pull, right? Pull, when we say pull, it pulls from the registry. Docker run, take the image, start a container from that. Right? And let's say we have made some changes to this container. We can save it back as an image and then push it back into registry. Okay. So this is onward flow. We can also define the return flow. From Docker registry, pull the images, from the images, create the containers, run the containers. And if you have made any changes to this container, commit them back as images, push those modified images onto registry so that someone else can use. Okay, this is a Docker file for, let's say, a simple Python application looks like. We'll see this later. Now, Docker is installed mostly by default. It should be installed on most of the Linux. No, I think Docker is very huge, not very huge, somewhat on the higher side, on the bulkier side of the applications. So by default, it's not installed. You will have to explicitly install it. But on CWS, right? If you're using Cisco CWS, it is already installed. So again, how do you check if Docker is installed or not? You say Docker universal version command nowadays. So if it is installed, you will get something like this. So it is installed. Now you want to check, do I already have any Docker images sitting on my system? Sudo Docker images. You get this kind of error. chmod 666 this file. Right, this is the executable file. Your Docker executable file is stored in this location when you install by default under var run docker.sock. Now sometimes what happens is the user with whom you have connected as, he will not be able to trigger this executable. So he needs these permissions. Right? 666 is like read and execute, RX. So we are giving all the executable permissions to this guy. So give this, which of course we have to perform as a root user. Now when we do Docker images, it shows that yes, I already have some images. I do one thing, Docker RMI. So when you install Docker afresh, it should look like this. Now Docker installation instructions are pretty simple and straightforward. You can refer to any of the websites like DigitalOcean or something to install Docker for your respective operating systems. Right. Normally, how it happens is most of these software can be installed using package managers like apt for Ubuntu, yum for Red Hat, and so on. Right? But obviously when you give this command like sudo apt install docker, where will it try to fetch the Docker installer from? From app's repository. App will have some online location which it calls itself as its repository, where all these packages are available. It downloads from them from there and installs it. Now obviously this app repository cannot contain everything in the world, right? So it does not know when you say sudo apt install docker, either it does not know where to download this Docker from because it's not there in the apps repository, or probably it has, but it's an older version of Docker, right? So normally what we do is like when we are installing software, we update the repository where Docker executables are available. Then we use sudo apt install docker. Nowadays, like apt, there is one more package manager tool called as snap, which has come up. Right? Snap is much smarter than apt, but we should not mix up snap and apt. Right? We should stick to one package manager because internally the managers, there'll be duplicates. If you install a package using apt as well as snap, the package gets duplicated in two different places. Now, when you are referring to, let's say Python, you install using apt as well as snap. It installs in two different locations. Now, when you want to run it, you don't know whether it is coming from this or that. So this can lead to confusion. But snap is like much smarter. Like you don't Snap can figure out. Snap has an updated version of most of the libraries. So you can simply say sudo snap install docker. It installs it. Okay, so that's about the installation part of it. Assuming that it's installed, you check whether there are any images already present using Docker images. Right, so there is nothing. So it is like this. Now, let's say we want to get. Suppose I don't have Python Office. Of course, I have it Office. Oh, it is not there. Is Python 3 there? Yeah, it is there. Okay. Suppose I don't have it, right? You can say Docker pull Python. It is pulling Python. Now, what are all these? 1, 2, 3, 4. We call them as layers. Layers in the Docker image. What is it doing is this command Docker pull Python. It goes, it when we give this Docker command, it knows that yes, I need to pull it from the online central repository. Right? It goes there, takes the Python containers, Python images, latest version. Right? So when I can also specify versions when I have multiple versions. Since I didn't specify any version, obviously it goes with the latest. Right? It found the latest version of Docker image and it is fetching it. Okay. Now these are images. When we say images, we said that the guy who created this Python image, obviously you would not have written all the pieces that are required for Python to work. Right? He would have borrowed the OS image. So that becomes the first layer. On top of that, he would have made some configuration settings. That becomes second layer. On top of that, he would have copied Python executable files, whatever is required for Python to run. So that would have become this layer 3, layer 3, layer 4, layer 5. And finally, he would have made some configuration changes. That becomes your this layer. So that's how the image contains layers. Any change that you make, right, becomes like an additional layer. So when we pull, all the layers come and sit in our environment as an image. So you say Docker images again. And it shows that yes, now I have the Docker image downloaded onto my system. Oh, it's 1 GB. Okay. Let's pull Ubuntu. Docker Ubuntu. Docker pull. Here they package a lot of things into Python, but you see this Ubuntu, it is just 77 MB, right? Which means whatever are the bare minimum uh, files and the settings and the system tools which are required for Ubuntu to work have been pulled and have been pulled into the image. You see that image is just 77 MB in size. So for a bare minimum Ubuntu to get up and running, we just need this sized Docker image. Okay, so that is about Docker images. So these were the images. We just pulled Ubuntu image, we pulled Python image, right? We did Docker pull Python. So from the third party, from the online registry, it came and sat in our Docker host. This is the machine where my Docker is installed, and this is the client or the CLI from where I was giving this Docker pull commands. Right? In my case, Docker client as well as Docker host happen to be one and the same system. Right? But the components wise, they are different. My CLI is where I'm giving those Docker commands is this Docker client part. The daemon which is running in the background, which takes these commands and executes them, is the server component of it. And the remote repository from where the images are being pulled is the third component. Okay. Now, how do I pulled Python image. What do I do with it? If I want to work with Python, I need to create a container from this image. Right, so I'll say Docker run. I want to give some name to my container. My Python. Right. From which image you want to start your container? Python. So it did something. I don't know what it has done. So let's check whether the container has been started. Right? For checking the images, we use Docker images. For checking the containers, we use Docker PS. Right? There's nothing. If you want to check current as well as past, we use Docker PS -a, show everything. So you see, it has created a container and it has also exited. Right? It started. It created a container and also stopped it because we didn't say that yes, give that to me in an interactive mode with the terminal so that I can interact with it. And so for that we can say using -it, -t actually, this is -it, which says that okay, when you are creating the container, create it in a interactive mode. Okay, it's already running, so I need to use a different name. In fact, you don't need this name. It will automatically assign some name to it. Now you see, we get Python prompt here, Python interpreter. We said I want to interact with it. It gave me an interactive way. Right? So this is my Python version which is running inside the container. I exit and do Python right. I actually have 3.10, but since I have a Python image, when I created a container based on this, I get 3.12. Okay, this is my local. This is coming from the container. Now I also had pulled Ubuntu. How can we check? Docker images. Right, Ubuntu is also there. How do we use it? Same way. Docker run Ubuntu. It starts, stops. Docker PS -a. Ubuntu started and stopped because I didn't ask it to make it interactive. Right? So to make it interactive, I need to say Docker run -it. Now I'm inside the container. And I asked Docker to create a container based on this image called as Ubuntu, make it interactive, which means I can work with it, and give me the terminal. So it gave me the terminal of the container. Now I am inside the container, which is like my mini VM. It was just 77 MB, right? The core operating system files which are required for this to work are provided, nothing else. You don't have, even VI editor is not there. Nano editor is not there. Nothing is there. INET tools, nothing is there. You can't check. Nothing will work. All you have is like a bare bones Linux, which is good enough, right? But I don't intend to use this as a replacement to my Ubuntu VM, right? This Docker Ubuntu image is ideally meant for acting as a base image for something else, right? Like the Python guy who created the Python guy. He needed a OS on top of which he can install Python and expose that as a Python image. So he would have taken one such either Ubuntu, or there are even more lightweight versions called as Alpine Linux and so on. Now I'll come out of my container. I'm back on my Docker host. Right? I had gone inside container. Now I'm coming out of the container. See these many containers. I created 3 containers. Since I didn't choose the name, every time it runs, it gives some random name and then starts the containers. Docker PS will show running containers. No container is running. Docker PS -a will show all running as well as exited containers. How I can delete exited containers is Docker RM, and either you can give this name, these names, or you can give these IDs, container IDs. Now you don't have to give this full name or full ID. If you want to give name, let's say just type part of the name and hit tab. It picks up and it deletes it. Suppose you don't have names. I mean, names are this thing, right? This first 3 letters CCB, Docker RM CCB, it will be removed. First 3 letters or first 4 letters will be enough. How do you know? Check down again. Docker PS -a. Docker RM C2B. To remove the images, we can use Docker RMI, right, which stands for remove image. Now, how you start a container, how you interact with the container, it depends on type of application that you're dealing with, right? We just saw OS in a container, a programming language in a container, right? Same way we can have a web application in a container. So the way you interact with the operating system vis-a-vis the way you interact with a programming language like Python, or a platform like Python, vis-a-vis the way you interact with a web application is totally different, right? Web application, you don't bother about the backend stuff. You don't worry about where is your application running. You would just get a URL, you will access it from browser. So you don't need to interact with the container, right? So such things where you have a UI or a front end or a web applications, those things you run them in background. But whereas these tools, like your programming languages, your operating systems, you want to interact with them. Those you start in non-detached mode, that is interactive mode. Okay, which is what we just saw. By default, it was starting in detached mode. It was just starting and stopping. We explicitly said start it in interactive mode. Now we'll pull a web server, Docker, pull engines. Engines is like a web server as well as a reverse proxy server. Docker images and engines. Now let's say you see the size, just 187 MB. So lightweight and right, I just created a random VM on that. I'm just running it. It runs. You create 10 VMs, you pull image on that, it runs. Right? Irrespective of the underlying system, as long as the underlying system has Docker, this will go and run properly because it goes as a container. Everything that is required for it to work is there in that. So we'll say Docker run. I don't need it in this thing. Run engines. Now with engines, what happens is it starts the web application inside the container. By default, the web page, the default web page of this default web server web server is available with containers IP address and port 80. But I don't know what is the container IP address. So what I'll do is do the port mapping. Now I want to access port 80 on container because my web server, Nginx web server, is running on port 80 of the container. Now, if I want to go into the container and access the port, I need the details like IP address or FQDN, etc. Right? So without getting into that complexity, what we'll do is you simply expose containers port 80 by mapping it to some other port on host. Right? Take some free port on the host where Docker is running, map it to port 80 on the container, so that when we hit the local host or the Docker host, the port which is mapped to port 80, the request goes to containers port 80, and whatever container response will be shown in on the port which I have mapped. Okay? So while starting, we also need to do port mapping. Otherwise, you will not be able to access the application which is running inside the container. So port mapping we do using an option called as -p, which stands for okay, do port mapping. Now IT, yes, sorry, 80, right? I want to map, let's say, port 80 on my system onto port 80 on Nginx. Let's check if something is not already existing on port 80. Is not. I didn't give port 80 because 80 is like the default port. So this as well as this are safe. So ideally, curl is like a command line option to check the web system. Ideally, I should have called it like this: HTTP localhost $80. 80 is default port. Even if I don't pass it, it goes there itself. HTTP is the default protocol. Even if I don't pass it, by default it uses HTTP. So that's why I can do this. Now, since my port 80 on the machine where Docker is installed, the host is free, I'll map it to port 80 with the container. Docker full -p. Sorry, run full. Docker run -p, do the port mapping, Nginx. Okay, it is running now. I didn't ask it to run in detached mode, so it's occupying my terminal, but it is running. So now go to hosts port 80. Host is the machine where I am running this. That is 2.1.0.1.0. And port 80 again is default, so whether we specify this or not, it's fine. So this page is actually coming from inside the container. But what have I accessed it using? I accessed it using the host. Right? So the request which I gave it to host colon port 80 was redirected to the container, and then container responded with this page. That page is just redirected back to me. I stop this. Ideally, my page should be gone unless it is being cached. Okay, this is not cached. Yeah, so I am not able to access it. Again started, but this time you add a switch called as -D. It says that start it in a detached mode, which means you get back the control. It started it, and you get the control back. Right? Which means it's not occupying your terminal. Application is up and running again. So this way, the way you interact with the different types of images differs depending on what type of this thing. Right? Suppose I pulled a PostgreSQL or a MySQL or a MongoDB image, and I started it. How do I interact with the database? There'll be some client which is used to connect to the database and then check out the tables, write queries, etc., etc. So the way I interact with those containers, those images and those containers will be different. The way I interact with programming language like containers will be different. The way I interact with OS variant images or containers will be different. Okay? So there's no single way. Okay, so that is about how to pull Docker images, how do you create different types of containers, and how do you access them. Now, suppose let's say I have an application So this is the way you can write a Python file, sorry, Docker file. You're saying, I need the base image, right? You can say 20 point, if you specifically want, let's say, Ubuntu focal, which is 20.04. So you can specify that. This we call it as a tag. Or we can say 22.04. Or if you just leave it, the latest image will be considered. Okay, take that. Then on that, you run this command, right? Take Ubuntu base image. Once you get that, you run this command apt update, apt install something, because uh, the fresh Ubuntu image, nothing would have been. I mean, even the apt repositories would not have been updated. So we do an apt update and install something. Then we are running. Okay, we are installing these Python 3.8 and pip, and then we are doing app clean, then removing the temporary directories, and we are running pip to install some Python packages. Okay. So it's basically taking a base Ubuntu image, installing Python, and using pip, it is installing these packages. So that's what this Docker file does. Okay. Now I want to create my own image. I'll say Docker build. Right? By default, the file name will be considered -p dot. It is something like saying use the current directory, which means in the current directory, it expects to see Docker file. If you give a different name, then you will have to specify the name of the file using some parameter. Right? Normally, we do this in their respective project directories, so there will not be any conflict. So we'll name this file as Docker file itself, and then we'll say Docker build. Yeah, I have to give an image name, which I didn't give. So it is doing all that. It is taking the base Ubuntu image, and then you see now it is executing this command, which means it is installing all that. Error failed to solve process. It did not complete successfully. Okay, some of these commands are failing. In this case, what am I doing is I'm taking Python as a base image. So within Python, right, there is a slim version of it, 3.8 Slim Buster, right, which is like bare minimum Python, which is required. Then I'm creating a folder called as /app, making that as work directory, copying requirements.txt from my local system into this into the container, then running these commands pip install minus requirements.txt is like in Python. Suppose I'll show you. Right. I'm here, not here. I have Python 3 installed, right? So I'll say pip freeze. Now the pip is like your apt, how apt is for Ubuntu, pip is for Python. And the pip is also like package manager. We install different packages using pip. Now all the package, if you want to see what all packages we have installed, right, we can use this command called as pip freeze, right? So for instance, in this, these are all the packages which are installed. Suppose this is my project directory. I install all my Python project dependencies. They become this list. Right? Now, I build my application here. Then I'll be taking my application running somewhere else. So when my program is running, obviously it will be needing all these libraries. Otherwise, it will throw error because you'll be using some commands from these libraries. And if the libraries are not found, it will throw an error. So what you have to do on the target system also, you need to install the same things. Nowadays, with everything being available on the internet, earlier we used to create build with these libraries also packaged. So build used to become very big, and that's why we had CDs. Of course, still there. I mean, CDs are not there, but still the software size is like pretty big in GBs, etc. And so shipping will be very difficult. It become very bulky. Instead, you simply say these are the dependencies that I have used. Wherever you are planning to run my code, you install the same dependencies, which means I just need to tell them what are the dependencies that I'm using. Now I'm getting these dependencies using this command pip freeze. Now I'll use this command, redirect it to a file called as requirements.txt. Now the name can be anything, but typically we keep it this requirements.txt. Created a file requirements.txt to a cat requirements.txt. Okay. So suppose you source yes, yes. So I moved into a different different Python virtual environment. I'll do pip freeze here. You see here the list of packages which are installed is different from the list of packages which are installed here. Right here it starts with Ansible, etc., 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 and ends with urllib, and here it is different, decrypt. Okay. But suppose I need these things here, right? So what I'll do, I have requirements.txt here. So I'll say pip install -r requirements.txt. It will install all those packages which are mentioned in this requirements.txt here. Okay. Same thing we are doing in your Docker file. Okay. So we are taking the local requirement.txt, copying it there, then running this command pip install -r requirement. So on the container, all these softwares will be installed, and then we are saying copy dot from dot the project directory from our project directory. We are copying all the files onto that, and then we are starting the server using this command. So when we start the container, this command will be executed, so our application will be up and running. Okay, so that was about how you go about creating. Now you can put any number of instructions. You just have to decide what all you plan to include into your image. But those commands like uh, from, run, work directory, copy, right? These are kind of action items, like what you want your Docker file to do, how you want it to create the image. Now you know like what are containers, what are images. So there are programming language images, there are web server images, there are Python application which we have just seen, right? There's a Python application which we have created. We can convert that into an image, right? And we have DB images. Now, typically in a enterprise kind of scenario where you are building some application software, it involves multiple layers, right? There's a UI layer, which is like your web. Then there's a middleware layer, your APIs or the application logic, and the database layer, which is typically your database. Nowadays, earlier we used to install these three on three different servers. UI on one UI server, front-end server, middleware on one middleware server, then DB on some backend server, and link these three, and then your application used to be up and running. But now your UI is available as a container, your middleware is available as a container, your DB backend is available as a container. So you can just take three containers, stitch them together, and you'll have your application up and running on Docker. Of course, it can also be accessed if it's a web application, just like how we have used this. You can access it from outside also. So we are talking about multiple containers working in tandem to make one big application. That is where precisely Docker Compose comes into picture. As the name suggests, compose, Docker Compose composes multiple containers to work together. Right? It will be an YAML file. Okay. So I'm saying that my application will consist of one web server, right? For which the base image is Nginx latest, And when this web server starts, it should expose port 80 in the container to outside port 80. And there is one more there's one more database which is involved. In my this is my web layer, this is my backend layer, right? So the backend layer is MySQL. Then its root password should be set as something secret, right? And the data should be stored in this, right? There's I'm taking a I'm creating a I'm taking this local folder and mapping it so that the data gets persisted, right? Suppose, so this is, it's like I have one container, I have another container. By using this, it's like whatever values I specify here, those I'll be using in my application here. So that is like connectivity. For my application to work, I'll be specifying the username, password, etc. Now I need to bring up these both containers together, bring down both these containers together, because now they form one single application. I'll be bringing up or down this entire application. So what I'll do is I'll say Docker, from wherever this Docker compose file is there, I'll say Docker compose up. So it's pulling the database image, then it'll pull the web image, it not only pulls the image, it also creates a container. Okay, this is what is orchestration, orchestrating multiple containers together. It says port is already allocated. This guy is still running. Yeah, it is still running. No, here itself. This guy is running. So yeah, my MySQL has been brought up because of this. So it's not started properly, so I'll bring down everything. I'll say Docker compose down. I'll say up again. So you see, managing multi devices is as simple as just using these commands like up, down. All the specifications have been pushed into my YAML file. Then all I need to say Docker compose up. And now my PLSQL, these things are running. Now it is running. Okay, so that is Docker compose for you. Docker compose is like a YAML file which specifies multiple images, and the interactions between them has been taken care by the respective images. Like we are not explicitly linking one image to the other, one container to the other. In the containers code, it will be referring to certain URLs, certain ports, certain environment variables, which are being set as part of the second container while starting. So that way, connectivity between them will be established and your application will be running end to end. Okay, we'll stop here. And what else do we have? Summer, there's nothing much. I mean, we cannot, of course, you can just look at the, you don't have to actually install it. And there's a Python APIs which are available, which we have already seen how to work with Python APIs. So you can just try it out. You have a GitHub page where you can check out the code. Okay, so kind of we are done, almost done with the things. So we'll have one more session for any doubt clarifications, etc. So you can, that we'll have on Monday. Right? Other than that, all the major components that we have planned have been completed. Okay. If no questions, we'll wrap up and meet on Monday. Bye.